Okay, 2.7, inverse of a function. So inverse functions are special functions that undo the original function's operations. Okay, the symbol for the inverse of a function is, it looks kind of like an exponent, but it's read at f inverse at x. Okay, so no, f inverse is the inverse of f at x. It is not an exponent. Okay, it doesn't behave like an exponent, it's just notation. Okay. Also, the biggest issue when when students try to find an inverse is they end up taking the reciprocal function, which is just like flipping the function, like 1 over, or flipping the numerator and denominator, and that is also not an inverse function. Okay. So what happens with an inverse function is we're exchanging the x's and y's. Okay. So in mapping notation, aka like in x, y, or f at x, and then like the range of f at x. Say, for example, we have the point 1, 1, then they're going to switch, and then obviously it's going to be 1, 1. Okay, if we have the point 2, 4, then the x and the y is going to switch, and we're going to have 4, 2. And if we have 3, 9, it's going to switch to 9, 3, and then 4, 16 is going to switch to 16, 4. Okay, so I want to highlight this. The domain of the function becomes the range, right? So the domain of f at x, all of the points are going to go from like the domain and they're going to go into the range. Okay, and then the range of f at x is now going to become the domain of like f inverse. Okay, it can be seen that the domain of f at x becomes the range of f inverse, and the range of f at x becomes the domain of x inverse, so that they switch sides. Okay, the functions inverse have this property. So the function at a equals b, then the inverse function at b equals a. Okay, and then that's what we're saying, just the x's and the y's switch. For example, f at 5 equals 13, then f inverse at 13 equals 5. So simply interchange the domain and range values. Okay, and then also to draw the inverse, all you have to do is swap the coordinates. And we'll take a look at that. Okay, so finding inverses numerically, the table shows ordered pairs to be the function. Okay, so just like random ordered pairs we have here. So we're going to determine the pairs for f inverse and then state domain and range. So instead of being -5, 0, we're going to have 0, -5. Instead of -4, 2, we're going to have 2, -4. Instead of -3, 5, we're going to have 5, -3. Instead of having -2, 6, we're going to have 6, -2. And instead of having 0, 7, we're going to have 7, 0. Okay, so domain and range, I'm going to put them down here. F at x, so the domain is going to be, and because this is discrete, we're just going to list the numbers. -5, -4, -3, -2, and then I have a 0. And the range is going to be, again, list the numbers because it's discrete. Oops. -0 to 5, 6, 7. Okay? Now, let's draw a line. What about f inverse at x? Okay? So if we actually take a look at this, like the x's in the inverse, we can list them again, and we have 0, 2, 5, 6, 7. Okay? If you take a look here, these two are identical. And then we have, for the range, it's the y values, y equals -5, -4, -3, -2, and 0. Okay, and that's how we do it using a table of values. Okay, finding inverses by graphing. So the graph of f inverse at x is the graph of f at x that's reflected in the y equals x line. So what this line is right here. Okay, this is true for all functions and their inverses. If you find the midpoint of each pair of points, so for example, this point maps onto this point. If you find the midpoint of like this line, it's going to lie right on that y equals x. Or if you this one to this one, again, it's going to lie right on that y equals x. Okay. Okay, so 2a, graph the inverse of the discrete function below, then state the domain of the function and its inverse. Okay, so first of all, I can create a table of values to make it really easy. Okay, so I get -4, 1. Let's go -4, 1. And let's do this as f at x and then be f inverse at x. Okay, that's going to map on to the opposite, 1, -4. Okay, and then -3, 1 is going to map on to 1, -3. -2, 2 is going to map on to 2, -2. -1, 3 is going to map on to 3, 1. -1. 0, 2 is going to map on to 2, 0. I'm going to continue the chart over here. 1, 1 is going to map on to 1, 1. Okay, because that's like right on this line, right? So that makes sense. And then I have 2, 0. It's going to map on to 0, 2. And then I have 3, -1 is going to map on to -1, 3. And then I have 4, -1. And that's going to map on to -1, 4. Okay, so domain and range. So the domain and the range are discrete. So this would be f at x. This is going to be domain and range of f inverse at x. So we can do XER such that x equals, and what we're going to do is we're just going to list the numbers. Okay, and they're going to be the same over here. X equals, and we're just going to list the numbers. So we got -4, -3, -2, -1, 0, 1, 2, 3, 4. -4, -3, -2, -1, 0, 1, 2, 3, 4. And if we take a look at, since this is the domain of f at x, it's going to be the range of f inverse. And if we look at the range of f inverse, -4, -3, -2, -1, 0, 1, 2, 3, 4, we can write down the exact same thing. So those ones are going to be identical. Okay, now the range, 1, 2, 3, we have another 2, another 1, 0, -1. So we want to put these in order. -1, 0, 1, 2, 3. Okay, the range of f at x is, we don't even have to look, and we just know that it's the domain of f inverse at x. Okay, graphing the inverse of a continuous function, a little bit different. So what I would do is I would mark down like key points. So I mark down 2 endpoints and then 2 kind of like turnaround points. Okay, we don't have to do the ones in between here. So let's do the same thing. F at x, we'll record the points, and then f inverse at x. So -4, 0 is going to map onto 0, -4. Okay, so those two map onto one another. And what I'm going to do is when I plot the next point, I'm going to connect them. Because what happens is you're going to have 4 random points and you're going to forget how they're connected. Okay, so this one's going to connect onto -2, -4. So flip these, -4, -2. So that's going to connect like this. Okay, and then from here, we're going to connect, instead of 1, 3, we're going to connect it with 3, 1. Okay, and then we're going to connect this, instead of 4, -1, we're going to connect this with -1, 4. And you can see how if we didn't connect them one at a time in order, it would get really confusing. Okay, so this is a continuous function because in order to draw f at x, we don't actually have to lift up our pencil, and the same for f inverse at x. So we can use like the crocodiles. Okay, so we have x is an element of the real number system such that, so the x's go from -4 to 4. Okay, which means the range of the domain of f at x is going to be the range of f inverse at x. So we can do the exact same one. Okay, now the range goes from -4 to 3. So y is between -4 and 3. So the range of the original is going to be the domain. Oops, but we have to mark it obviously with an x. Like that. Okay, finding inverses algebraically. So there's a couple steps that we have to take. First, we're gonna replace f at x with y, so just simple notation. Okay, then we're gonna switch the x and the y variables. And then we're gonna re-isolate for y, and then instead of writing it as y, we're gonna rewrite it again in function notation. So here's an example. So a is linear, okay? So we have y equals 4x plus 3. Now, exactly where we see the y and exactly where we see the x, we're actually going to switch these variables. Okay, now we just re-isolate for y. Okay, so we have x minus 3 equals 4y. Divide out the 4. Okay, and I'll just put it up here. I get y equals x minus 3 over 4. And then we have to write it as f inverse of x equals x minus 3 over 4. Okay, so the inverse of a linear function is also linear. Okay, so let's try this one. This is a quadratic. So y equals x squared minus 1. We're going to change this to x equals y squared minus 1. Bring over the 1, the -1, it becomes positive 1. And in order to reverse the squared, we're going to root both sides. So we're left with y equals root x plus 1. Okay, but when we root a number, we actually have to take into account plus and minus. And I think we're going to investigate that one on the next page a little bit more in depth. So f at x inverse equals the plus minus of x plus 1. The reason why we need the plus minus is because we have a parabola like this. It has two chunks here, okay, two parts of that graph. So when we have a root function, we have this part and we have the reflection part, okay, positive root x, negative root x. So we need both parts. Okay, scroll down. C is also linear, okay, just looks a little bit different. Y equals 4x plus 3 over 5. Let's exchange the x and the y. And now just isolate for the y. So I'm going to cross multiply. We get 5x equals 4y plus 3. Okay, we're going to bring this plus 3 over. It's going to become -3. And then we're going to divide out this 4. So we get y equals 5x minus 3 over 4, but we have to use function notation. So f inverse at x equals 5x minus 3 over 4. Okay, Again, another linear function. Now let's find the inverse of this root function. So y equals negative root x plus 2. We're going to switch. So we have x equals negative root y plus 2. Okay, first bring over this plus 2, and we're going to get minus 2. Then we're going to have to divide out this negative 1. Okay, so this goes away and this goes away. And if we divide each of these by negative 1, it's just going to negate them. So we get negative x plus 2. We just changed the signs on these, okay? So I get negative x plus 2 equals root y. I just rewrote it. Okay, how do we get the root off the y? So this is what we have to remember. What we do to the left-hand side, we do to the right-hand side. So we actually have to group these and then square it like that. Okay, so we get y equals bracket negative x plus 2 squared. So then we can just write that with function notation. And all we're doing is rewriting it. Okay, I'm going to move this one up. Okay, so here's a note. For algebraic inverses of quadratic functions, before we interchange the x and y, we have to rewrite in vertex form. So essentially what we're looking for is we're looking for a function with a y on the left and some function of x on the right, but the x only written once. So there's an issue when we have an x squared and an x. Okay, it gets complicated and messy. So let's rewrite this. Let's rewrite this as y equals 2x squared plus 16x plus 29. So let's first complete the square, because then what we get is we get this quadratic in vertex form. And what happens is then we only have one y and one x on each side. Okay, so divide out the 2. And we get x squared plus 8x. And we're going to take that 8x term, side of our paper, divide by 2, and then square it. Okay, so 4 squared is 16. So we get to x squared plus 8x plus 16 minus 16 plus 29. So when we take this negative 16 and we want to bring it over here, we need to multiply it by 2. Okay, we're left with our trinomial in the bracket, x squared plus 8x plus 16. Okay, and then we get negative 32 out here. Okay, so we get plus 29 minus 32. So we can go ahead, the last part of completing the square is we're going to factor this. So we get x plus 4 squared, and we're going to add these. So we're going to get minus 3. Okay. At this point, we have one y on the left-hand side and one x on the right-hand side. Now we can actually find the inverse. Okay, so let's go ahead and switch the x and the y. So we have x equals y plus 4 squared minus 3. Okay, bring over the negative 3. We get x plus 3 equals y plus 4 squared. How do we get rid of the squared? Root. Okay, so just remember we have to root the entire left-hand side. So the root sign goes over that positive 3 as well. Okay, so now we have x plus 3 equals y plus 4. Bring over that 4. And it becomes negative 4. And then that y is isolated. So now we can sub back in the f at x, that function notation, for that y. So we get f at x inverse, or f inverse at x equals x plus 3 and then minus 4. Okay, and then don't forget the plus minus. So there are two functions that I want to highlight, and they're actually inverses of each other. So the square root function and then afterwards the inverse of a quadratic. So here's the thing. Inverse of a square root function. So if we had this equation for f at x, first of all, sketch f at x and then f inverse at x. So we know that like our big vertex is going to be at 1, 0. because this is just going to move to the right 1. Okay, so 1 and then instead of 9, it's going to be 10. Okay, so this is the original. Okay, so this is f at x. And now inverse is going to be a reflection here. So instead of being at 1, 0, it's going to be 0, 1. 2, 1 is going to be 1, 2. 5, 2, it's going to be 2, 5. And then 10, 3, it's going to be 3, 10. Okay, this is going to be f inverse at x. Okay, determine algebraically. So if we wanted to determine algebraically, we sub the y in for f at x, and then we switch the actual y and the x, and then we just solve. Okay, so square both sides. So we have x squared equals, the squared and the root cancel out. And then we're left with y minus 1. Okay, and bring that negative 1 over, and we get plus 1. Okay, substitute back in the function notation. So f inverse at x is x squared plus 1, which we know is a quadratic that's moved up 1. Okay, so is f inverse a function? So if we're taking a look at it like this, so this is B, this is A. Okay, so C. Okay, so yes, it is a function because it's just a quadratic, right? X squared. It is a function. Okay, so here's the thing about the having this as the equation for the inverse. So if we actually graphed x squared plus 1, like it wouldn't look just like this. It would actually look like this. Okay, so it would be like the full quadratic, but we actually don't have this side to this, like the reflection of the root, right? So we actually have to put a restriction on the domain. So the restriction on this domain would like have to be x has to be greater than or equal to 0. And what that's going to do is it's going to take this quadratic and it's going to start it at 0. And it's just going to be like that right wing of it. And like that's the part E. We would have to restrict the domain of f inverse so that f inverse of x is actually a function. Okay, when we're going through this algebraically, you have to be able to be aware of this without actually seeing it graphically. Okay, so D, if we did domain and range of the inverse, okay, now we have to restrict x is greater than or equal to 0. This is for the inverse. And then y is going to be greater than or equal to 0. Okay, now this like domain and range are going to mimic more like the domain and the range of the root function. Okay, now on the flip side, inverse of a quadratic. So say we're given this quadratic equation f at x equals x squared plus 2. This is just a parabola that's moved up 2. Okay, so if I have a normal parabola, it's going to move up 2. It's going to be there actually. Okay, and then that's going to be off the grid. That's okay. Okay, so this is our normal parabola. Okay, so this is f at x equals x squared plus 2. So let's actually take a look at what this inverse would look like. Okay, so instead of 0, 2, it'd be 2, 0. And then 1, 3, and negative 1, 3. 3, 1, 3, negative 1. And then I'll just do 2 more points. 2, 6 would become 6, 2. and then 6, negative 2. Okay, so if we're actually talking about the inverse, we have to consider both arms of this quadratic. Okay, so now algebraically, if we were to write this out, we're going to switch the x and the y, and then bring over that positive 2, it becomes negative 2, right? So y squared, we root both sides. So at this point, we have y equals x minus 2, which is f inverse at x equals root x minus 2. Now, this only takes into account, like this right here, only takes into account that positive arm of the root x function. We must take into account both the positive and the negative in order to get the full inverse of x squared minus 2. Okay, so f inverse at x is not a function. Okay, doesn't pass the vertical line test. We can see that 2 y's satisfy each of these x's where it's defined, except for this point here. But all the other points from above 2 y's satisfy each x. Okay, so state the domain in the range of f inverse at x. Okay, the domain is going to be XER such that x is going to be greater than or equal to 2 and y is going to be